stream. Fingers. All right. Get my attendance just in case whenever you test positive and they come back to me and say, "Ooh, did they sit around?" I don't know why they do that. So apparently they do ask. If you fill out the form and you test positive, they ask you who have you been around and so forth. But I've never been asked. So I was told it's pretty good about reporting who they've been in close contact with. It's good. It's good. And look up my attendance. May or may not be correct. All right. So I asked you to do this one sample t-test, practice number 2. These 4 ponds for mosquito fish. We ended a little early, so we can talk about it. Give you time to actually do this. So let's go. All right, mark down. So new. Just open it up. So everything's empty. I'm just going to go ahead and run my import. So it is available. Note that all of my variable names are called pond 1, pond 2, pond 3, pond 4. So I know I read it in correctly. All right. So question number 1. We asked, is the sample mean equal to, I should say, is it not equal to 24.5? Is the mean equal to 24.5? So with that question, it implies then that the alternate is that they're not equal. So those of you just watching didn't see it last time. This actually is the code that gives us the not equal sign, which is pretty cool. So when it knits, it should report it as not equal. So it's a two-tailed test. We have a vector of data. So we can use, since we actually have the vector, we can use t.test function. And t.test, we do mosquito fish $pond1, that's our vector. And I specified mu equals 24.5. So if you were running into problems and you just did mosquito fish $pond1 and then 24.5, what was the error message? Cody.
I'm sorry?
What was the error message that you had? That out. But if you did it this way, you remember?
I think it wasn't reading it.
Yeah, not enough y observations. So it read this as being like an x and a y, because there's more to this t-test function than just the one sample t-test. So if I just go and view the help file for the t-test, all right, student's t-test performs 1 and 2 sample t-tests on vectors of data. All right, that's what it does. And it's going to look for, if we use t.test, it's going to look for our x vector, and then it's going to look for all of the other options that we have in it. That's what our ellipses stand for, this, the dot, dot, dot. So, the default is just x, and then y is null, so that we didn't give it anything. But if we just gave it this number, like this 24.5, it goes in order. So that's the second item that we give it. It looks for y, X and Y have to be the same length. They're not, because Y, this 24.5 is a single number, whereas this pond 1 is a vector. So what we actually want to do is specify the mu. And this is where the mu appears here. And the default is that the difference is 0. And that's you're going to see when we do our 2-sample t-test, that's what we typically test. Is the difference in our means equal to 0? And if it is, then we know the means are equal. All right, so what we have to do in order to get this to run properly, we actually have to do mu equals 24.5 so that R knows that we're running a 1-sample t-test. And when we do, I get my output, gives me everything that I need. So here's my write-up. And this is just one example write-up. Yours could be a slightly different, but all of our write-ups should have all 5 things. Should have our conclusion or the interpretation. So the mean is not equal to 24.5. That's our conclusion. Our test was a t-test, our t-statistic, our test statistic. That's there, our degrees of freedom, and our p-value. And that information was all derived from the output of our test. All right? So the t-test has all 5 requirements. Question? Did you do pond 2 and pond 3 and pond 4, hopefully? All right. So yours could be, again, your write-up could be a little bit different, but we still need all 5 requirements. And when we get to, write-up, when I grade the write-up, I'm looking for all 5. I'm looking to make sure that you have all 5. And I'm making sure that you actually did the correct interpretation. Right? So if you say the mean is equal to 24.5 because you got confused and said, oh yeah, it's less than 0.05, that must mean that they are equal. Yeah, you'll lose like a full point there because the interpretation is wrong. You really need to know what that greater than 0.05 and less than 0.05 means, what that cutoff means. All right, question 2. Pond 2. I asked, is the mean equal to 25.15? So again, I didn't set direction, so our alternate is that it's not equal. And EQ. So again, I'm just going to update the pond. We're working with pond 2, and our mu is 25.15. I run it, I get this output. Based on the output, is it equal? It is. Mean is equal to 25.15. Our conclusion, interpretation, our test statistic, degrees of freedom, p-value, all 5 things. I'll also note, check the rounding. All right. I'm also paying attention to rounding. Our test statistic t should go to 2 decimal places. That's our standard. 2 decimal places for a test statistic. For a p-value, we're greater than 0.05, so we can go to 2 decimal places. Pond 3. I asked, is our mean smaller than 25.05? And this is where I see some students mess up. All right. I asked the question, is the mean smaller than 25.05? That doesn't mean that the null hypothesis is the mean is smaller than 25.05. We can't test that. The only thing that we can reject is that it's not equal to a certain value. So our null hypothesis is always going to be that our mean is equal to that value, in this case 25.05. Our alternate then is that our mean is less than this. So if we're going to conclude that the mean is less than 25.05, we first have to demonstrate that it is not equal to 25.05. If it's not equal to that, then it's going to be equal to then it's going to be smaller than 25.05. So same type of thing. I have my vector here, I specify mu, but now since we're doing a one-tailed test, I'm going to use alternative. And I'm going to use alternative equal less here. Why less? Because that's our alternate hypothesis. We're saying that our mean is less than 25.05. And I get my output. So again, we have all of the output that we need. We look at our p-value for our conclusion greater than 0.05. Which means we failed to reject our null hypothesis. That means that our means are equal. So going back to our question, Was it less than 25.05? No, the mean is not less than 25.05. In fact, the mean is equal to 25.05. That's what we would conclude. We got our t-test, our test statistic, degrees of freedom, and our p-value. What happens if you messed up? What happens if you accidentally said greater because you couldn't remember, is it less or is it greater? Which one do I use? Look what happens. When we say greater, a couple things happen. One is our p-value. P-value jumped up. And sometimes the p-value is going to be like 1. All right. Second thing, note, our t is negative. Anytime we have greater, it should be a positive value. T is a negative value, that means we kind of messed up. We should fix it. All right, so if that t is negative and we're doing a one-tailed test, we should really be doing less. All right. On 4, is the mean greater than 23.75? Same type of deal. Even though the biological question asks, is the mean greater than 23.75? That is not our null hypothesis. Our null hypothesis is always that it's equal to some given value. So our null here is that our mean is equal to 23.75. Our alternate then is that it's greater than 23.75. So made my updates. This time we are using greater. And when I run it, I know that it works. I know that I used it correctly because I've got my t that's a positive value. Our mean is greater than our predicted value. All right, now what's our conclusion? Look at our p-value, it's less than 0.05. Therefore, we reject our null hypothesis. We know it is not equal to 23.75. And this concludes that our mean is greater than 24.5. We have our t-test, our t-statistic, degrees of freedom, and our p-value. Rounding, all properly rounded. Questions? No? All right. Move on. Not too bad, right? Assumptions. When we did our t-test, I gave you the 2 assumptions that we had. What are those? Number 1 is that our data are random and independent. All right. We normally plan for this based on how we collect our data. So as long as we have good collecting methods and we get a good randomized data set that's unbiased, all right, we normally satisfy this assumption. It's random and independent. All right. Occasionally we might violate it, in which case you probably know that you're going to violate it before you start the data collection. All right. But most of the time, we make sure this is true with our data collection process. The second one, data are normally distributed. That can give us problems. All right, because before we can run this test and have faith that our results are correct, we have to check this normality assumption. All right, so recall, when we did our transformation, we took our x bar minus the mu divided by the standard error. If we use the population level standard deviation, that approximates a normal distribution. That was our z. But in this case, if we use our sample standard deviation, this transformation now approximates a t distribution with n minus 1 degrees of freedom. This holds true only if our underlying data set is normally distributed. If it's not normally distributed, then this does not hold true. And it means then when we use this t distribution to come up with the p-value, we're coming up with the wrong value. Our t no longer follows that t distribution. All right? So here's an example. Here's a skewed sample. I created a skewed data set. This is our skewed data set. Okay, my image is this. And then from that skewed data set, I generated some t-observed values. Okay? From a bunch of skewed data sets. Now, we know it's skewed, so this does not hold true anymore. This assumption does not hold true. So if we calculate a bunch of t's from this skewed data set, this is what we get. And this overlay, this blue line, that's not a normal curve. That's a t-distribution. Note how we don't follow it. Our points, these middle of the bars, should fall in the middle of the line. And they don't. We've got too many values to the left of our curves. And that means then, if we calculate a p-value, an area under the curve, and let's say it's down this area here, we're under counting our values. We get an area under the curve that's less than what the actual distribution is. If we're up here, let's say this is our cutoff, we're going to have a larger p-value than what we actually should have, all because our underlying data was not normally distributed. So when we run these tests and we have these distributions, these requirements, we really have to check them before we can run our tests. So how do we check them? Well, we've already done this. All right, we've already done this. I think we've already had an exam over it, right? So when I get an email that says, I don't even know how to do this, it says check for normality. Man, I want to go back to that exam and say, I'm going to just start marking off. Say, even though you got it right, no, you obviously don't. I'm not looking at anyone here. All right, so quick review. All right, quick review. We're going to just breeze through this because this is all repeat. So we had our options. Graphical was histograms with the normal curve overlay, QQ plots, and Shapiro-Wilks normality test. All right. Just histogram with an overlay. Strengths is that it's quick and easy. I typically do this anytime I work with a data set just so I can look at it. And again, I said this before, when you make a histogram and all of a sudden you see this bar that's way out there, it tells me that I screwed up data entry. All right, so it's just kind of out of habit where I make a histogram just to check my data set, just to see what it looks like. All right, you can sometimes identify skew, kurtosis. Outliers is a big one. It's that bar that's way out there. Multimodality is very easy. So multiple peaks, that tells me something. That also gets revealed in a histogram, right? But all of this stuff really only applies to a large sample size. When you have sample sizes of 10 or 20, it's kind of hard to see some of this stuff. All right, so this is kind of the weakness. So for Pond 1 data, this is kind of how, so the example that we'll use is Pond 1 data, and again, this is how we did it. I think on an earlier slide, I highlighted some stuff to use, and I changed some stuff, but again, with our curve, this V kind of emphasizes all these things that you can use. I did it with the T distribution. You're going to see me do this with an F distribution later on as we get to the ANOVA and so forth. But here's our histograms of Pond 1, right? And we can look at the histograms, and does it look kind of normally distributed? Well, when we overlay a curve, when we pick the correct number of bins, maybe, maybe not. Kind of hard to tell, right? It's judgmental. So I don't think I'd rely on histograms a whole lot to determine normality. In fact, my recommendation is just to go ahead and do those quantile plots. The quantile plots that I like to use is the function that's in our car package. All right. So this makes our quantile plot, making it from the vector. This has options. We can do a quantile plot versus a T distribution or F distribution or chi-square, and you'll see me do some of those as well. But for normality, the default is graph it against a normal curve. All right. So the strengths of this is that it's very easy to perform. R does it. QQ plot's a simple function to run. Weakness is that there's no p-value to report, and some people really need to see a p-value. And I've run across that too, and it's like, you know what? No, you don't. This is good enough. This is good enough. All right, so this was pond 1. So where the histogram was kind of tough to make a concrete judgment, I think with a QQ plot we can definitively say, yeah, this looks normally distributed. Why is that? Because all of our points fall within our confidence interval. Minus these at the very extreme end, but that's okay. That's okay. So if we're going to rely on quantile plots, how do we report it? Just something like this. Quantile plot suggests that fish lengths from pond 1 are normally distributed. All right. For a quantile plot, we don't have a test, so we're not going to have a test statistic or degrees of freedom or a p-value. All right. So all that we have is an interpretation and what test was used, or in this case, what method was used. And in many cases, it just right in the method section of the paper or in the poster, I would say normality is checked using quantile plots. All right. And then if I'm going to do some tests because we violated normality, that's when I get to the results, that's when I would say, well, because the data were non-normal, we had to do this alternative method. And we'll talk about those too. Here's my cursor. All right, Shapiro-Wilks test, that will give us p-value. Again, pretty easy, Shapiro.test. It gives us a test statistic W that we would report. All right. This is the one time when I'd report this test statistic to 3 digits, all right, instead of 2 digits. And it also gives us p-value. So, you know, for that person or those persons that want to see a p-value, yeah, you can do this, but note that the major weakness is that it's strongly influenced by our sample size. So if we have sample sizes less than 100, you might not detect non-normality. If you have sample sizes above about 300 or 500, it's going to start detecting some of that non-normality that we can ignore. So some of those where we'll have some points fall outside at the ends, and we'll look at a QQ plot and say, yeah, that's going to be okay because it's a small number of points and they're at the extremes. Shapiro-Wilks may pick up on those and say, no, this is non-normal. All right. So I say avoid using this as an assessment of normality unless you're required to do so, unless a reviewer says you have to do it. All right. So even for pond 1, it gives us a p-value of 0.07. This is a case. All of our QQ points look good. It's just what, 2 or 3 points that we're outside. Look at our p-value there. So we're kind of on the verge of claiming non-normality. If we are going to report the results of this test, same things hold true. We report our results or we report our interpretation. We report our test that was run, Shapiro-Wilks test. We report the test statistic and the p-value. So it gives everything that we need. Shapiro-Wilks test, our test statistic W, and our p-value. It doesn't have a degrees of freedom. Right? No degrees of freedom for this test. So that one is none. So we don't have anything to report. All right, so pond 1 is normally distributed, which means when we go back to our t-test results, this, go on. So these results, I'm going to say, can be trusted because we know that data are normally distributed. What I want you to do is assess normality for pond 2, pond 3, and pond 4. See if any of them are non-normal or appear non-normal. And then if they are non-normal, go back and look at our results, look at our conclusions here, and see, kind of figure out, do you think these conclusions can be trusted or not? All right? So I say let's do all 3 as a review of testing normality. No, you don't have to do all 3. We'll save you some time. I think we've already had an exam on it. We're going to be doing this a lot moving forward. Did you get them? Yeah, you got them? Assumptions of a t-test. So we have two assumptions. Data are random and independent. We plan for meeting this assumption based on how we collect our data. All right, so with all of our statistical tests, with all of the ones that we cover, this is one of our assumptions. Obviously, there are tests where this assumption is violated, and we know it's going to be violated. All right, we know it's going to be violated. So those are specific types of tests, like a time series test. We violate that because the temperature of today is correlated with tomorrow's temperature, unless you live in Texas, and then it's just like completely random, right? Is it 90 degrees yet? 70 decided? Unbelievable. Now it's a high of like 40, 39. I left the house. Crazy. All right. Second assumption is that data are normally distributed. I should say, with our tests that we cover, when I ask, list the assumptions of the test. Data are random and independent is basically an assumption for all of the tests that we cover. All right. Data are normally distributed. This will be an assumption for most of the tests that we do. Not all, but for most. And this holds true for our t-test. So if we're going to check for normality, I'm going to use QQ plots. So first up, load my car library. It's already loaded. Pond 2. Here's my QQ plot. Run it. I look at that. So here's my QQ plot. What do you think? Is this normally distributed or not? Yeah, I think it looks so. This looks normally distributed. So, you know what would be our write-up? Oops. Yep, something like that. Again, we state what we did, QQ plots, and we state our conclusion or interpretation. All right, so if we're normally distributed, can we trust the results of our t-test? Yeah, we can. Pond 3. QQ plot, we get that. Does that look good? Yeah, I think so. So, I say the same thing. I'm just going to copy and paste and just change it to pond 3. Right up. Just pond. Whoops. Did I say pond? Is that pond 1? Pond 2. Pond 2 is normally distributed. Pond 3 is also normally distributed. I think we're going to be good with that. And Pond 4, what do you think? Yeah, I think so. I think this looks okay. Right? Few smaller sample size, definitely. Histogram would be a lot harder to judge. Yeah, we've got a point outside here and a point outside there, but overall, basically all these points fall within our confidence interval, especially the ones in the middle. So, yeah, I think this is also normally distributed. So, these 4 ponds, yeah, they all seem to be normally distributed, so the results of our t-test could be trusted. All right. So just as a review, QQ plots, go for those. Small percentage of points could fall outside at the ends. Those are okay, but the middle points are not. So were any of the assumptions violated? No, I don't think so. All right. So if they were violated, if we did violate normality, then what do we do? All right. Obviously, we can't continue with the t-test because the results aren't going to be valid. All right. Yeah, we'll get results. We'll get a p-value, no problem. But our conclusion, interpreting that p-value, could lead us to the incorrect conclusion. So what do we do if we violate our assumptions? Well, if we violate independence, that's going to be beyond the scope of this course. All right, there's plenty of things that we can do. Plenty of things we can do. What are some examples of when we violated independence? Let's say we do, let's say SAT scores. All right, that's a classic. And we look at SAT scores between different, let's say SAT scores of counties, maybe? Counties in Texas? Or just, let's say, regions, east versus west, all right? Our assumption is that each of our SAT scores are independent of each other, and while the individuals are independent, you can actually see violations of this because individuals that were from more affluent areas or individuals that went to what are considered better quality schools tend to exhibit higher SAT scores than those that aren't, that don't go to those schools, that aren't in those affluent areas. So we violate assumptions, and there's ways to get around that by kind of analyzing our data based on their groups to see, okay, well, if we kind of standardize where students went to school, standardize their socioeconomic status, then we're allowed a better comparison of those types of scores. That's going to be beyond the scope of this course. Graduate course, though, we may be getting to this. What about violation of normality? This will be the one that's most commonly violated. Well, we've got 2 options for a 1-sample t-test. All right. So our goal is to do a 1-sample t-test. We check normality. We violated normality. What can we do? Option number 1 is to perform a non-parametric test. All right. So the t-test is a parametric test. That's what it is. We assume normality. These non-parametric tests do not make that same assumption. They don't assume normality. Our test options are going to be a Wilcoxon signed rank test or a sign test. All right. These are two different non-parametric tests. Now, the downside of these tests is that we lose power. We lose the ability to detect a difference when there really is a difference. All right. So if we think our mean is equal to some number, it's going to be harder for us to actually detect when it's not equal to that number. All right. Conditions for this. Wilcoxon signed rank test requires that our data are symmetric around the median. All right, basically equal distances around the median. If we violate normality, that is probably the assumption that we're going to be violating. All right. Most of the time, if we violate normality, we're not violating it because we're leptokurtic or platykurtic. Typically, we're violating it because we're skewed, which means we're not symmetric around the median. So because of that, I don't recommend doing this one at all. All right? The sign test is going to be the one that we'll talk about. So the sign test doesn't really check the means. It actually compares medians. And it tests if the median of a sample equals some hypothesized value. So t-test was interested in comparing a mean. The sign test now is going to be comparing a median. Kind of two different things, right? Kind of two different ideas. Now, if we're normally distributed, our mean and the median are the same thing, which is kind of why we say that we can do this non-parametric test. But note that we're comparing medians. We're not going to compare the means. The assumption of this sign test, again, random and independent samples, all right, it's going to hold true. But then the other thing is that we need more than 5 samples to do this test. And you're going to see why, because we're going to use a binomial distribution to calculate our p-values. So these are option 1s, and I'm going to say that option 1s really aren't that good. If I violate normality, and I'm doing a 1-sample t-test, what I'm going to do is this option number 2, which is bootstrapping. I'm going to generate a 95% confidence interval using bootstrapping. All right, questions? Can we do these in R? Yeah, well, Cox's sign rank test is in R. But again, it's not recommended, and because of that, I'm really not going to be introducing that, showing you how to do that. Bootstrapping, or is a sign test in R? Yes and no. All right, you'll see how we do it. We use some of the functions in R, and then I actually give you a script. I give you a function that will do it for us. What about bootstrapping? We've already done it. We've already generated bootstrap confidence intervals, and that's exactly what we're going to do with this bootstrap. We use our randomization scripts. We generate a confidence interval, 95% confidence interval, and then from that confidence interval, we see if that interval actually captures our hypothesized mean. If it captures that hypothesized mean, then we conclude that our means are equal, that our mean is equal to that value. If our bootstrap confidence interval does not include that hypothesized mean, then we conclude that our sample mean is not equal to that value. So it's very easy to calculate in R. We've got the script, and we'll see it again. And it's also very easy to interpret. If our interval doesn't include that hypothesized value, our mean is not equal to it. All right. The downside is that we don't have a p-value, and again, some people are stuck on a p-value. This is very legit. With our bootstrapping, we can also do a bootstrap t-test, which is a t-test, but we generate our own t-distribution, which won't follow the underlying t-distribution that's in our tables. All right, we're going to have to randomize our data, and it's a little bit more involved because we have to transform our data so that that null hypothesis is true, and then we have to do all of our bootstrapping. It's a little bit more involved. We're not going to do this because any result that we get from a bootstrap t-test will match the results from a 95% bootstrap confidence. So I kind of look at it as if it's easier to do something and it comes up with the exact same conclusions, do that which is easiest. And for us, it'll be the bootstrap confidence. All right. So we're at 11:42. Real quick, introduction to the sign test. All right, so the sign test, again, is going to test if a median is equal to some value. That's what it's going to test. All right, we're not comparing the mean. And the way we go about it is basically compare each of our individual values and say, is it greater than the median, less than the median, or equal to the median? So what we're going to do is convert our individual data points to a plus or a minus. Plus or minus or 0. All right, if they're 0, they just kind of drop out of our data set, and then you've got a bunch of pluses and minuses. Well, if our median is equal to some hypothesized value, then we should have an equal number of pluses and minuses in our data set. We should have an equal number of values above the median as below the median, which then defaults kind of to a binomial test, which is the probability of getting a positive actually equal to 0.5 or not? All right. So what we're going to do is I'm going to kind of go over this. I'll use the board and kind of show how we do some of this by hand. And then I'll introduce how to do it in R. Note, our assumption is that it's random and independent. It's going to hold true for our test. But we need more than 5 data points in order to do this test. If we have 5 or less, don't even try. It's not worth it. All right, so what we'll do is we'll stop here. Before everyone signs out, though, note our homework assignment. So I believe it is posted. Yep. This is our homework assignment. This gives you practice doing t-tests and z-tests. We don't have vectors. We don't have a vector of data points yet. But what I want you to do is look at this. Look at this homework assignment. And the very first question on this asks, will you use a one-sample t-test or a z-test? And that is the same question for each of these. So what I want you to do, we're going to make this assignment, I think, due on Wednesday. Again, by the end of the day on Wednesday. But for lab, we're going to go over A's just to make sure everyone's doing the correct test. Right? And this will be like on our next exam, you'll have a section like this, just like we had with the binomial Poisson distribution, where I said, what distribution would you use? We'll have something similar where, what test would you use, a t-test or a z-test? And that's part of this course, is looking at what type of data we have and figuring out what test is most appropriate for it. All right, so we'll do that in lab. So look at it. You got 5 minutes now, and then we'll do like 5 minutes at the very beginning of lab that you can look at it, come up with your answers, and then we'll talk about it. And I don't know how to do like a poll other than doing it in Blackboard Collaborate. So what I might do is we may open up Blackboard Collaborate just so we can have the poll, and then everything becomes anonymous as to what your choice is for each of these. All right? All right. We're done. We'll come back at 2, and we'll talk about the sign test. We'll go through scripts. You'll get some practice on sign tests. Let's do bootstrap and confidence intervals again. Then probably won't get to bootstrap confidence intervals today. Let's see what we get. All right. See you too.